All right. I think we can go ahead and get started here. Cool. So welcome. It's the data analytics and machine learning and industrial IoT. I'm Scott Poulin. I'm a principal technologist at Object Partners, an improving company. I specialize in machine learning and artificial intelligence. Been total professional software engineering has been around 10 plus years. Healthcare, financial, banking, academic, and then nonprofit and state and government. And then primarily, a lot of it was in the railroad industry, kind of where a lot of my IoT and industrial IoT came from. So, but been programming and software development for over 17 years now. So, quick overview. So the IoT device we're going to go over today is something called a wheel detector. It's commonly used inside of the railroad industry and a lot of different applications for it. They're located pretty much all over the United States, just mostly due to how they're used. Outside of that, we're going to go into the raw data that typically comes in. So this raw data is kind of unique to this project that I was on, just because it was fed in different ways than normal. There's a lot of different ways that this data is actually fed in. And then the data pre-processing we kind of had to go through, and then data analytics that kind of went into it to really understand essentially how we were going to solve the problems that we were trying to solve. And then how machine learning kind of fell into this and how we were able to kind of use it. It was a very kind of one-off case, and it was kind of a stretch to try to use it, but we wanted to try to include it just to show that we had some sort of ability to predict certain things into the future. So then we'll kind of go into the architecture, what it started out with prior to any sort of technology and what kind of pains and struggles that occurred there. And then the first iteration architecture, and then lastly, the streaming architecture. And then the kind of the results that occurred because we put the new architecture in and what came out of it. And then finally questions after that. So wheel detectors, play this quick little video of it. So essentially, as the wheel kind of rolls over it, it sends these signals through two, essentially these heads is what we'll call them. And you'll probably hear me refer to them as heads going forward. But essentially there's this head 0 and head 1. And they essentially, as the wheel rolls across it, there's a magnetic field that triggers and essentially sends a signal out telling you that the wheel is at this point in time over the specific device. And so it's really nice because it can help you tell that something is there on the rail, or you can even predict speed to a certain degree. And then also it's easy to tell the direction of the rail car. And then it also, it's just more used as a supplement to other devices. And there's a central processing computer that essentially uses all this data to help it make decisions when going through and being able to make decisions on what it needs to do, essentially. So, and here, so what I'm essentially referencing here is this is where I primarily use them at in this type of setting. So this is something called a classification yard. Essentially, the cars will come rolling down this hill and they're spread out to these individual smaller tracks to kind of essentially build new trains and have them go out later on. But essentially, these wheel detectors are located through all out this area down here. And so you can use it to kind of tell when they're in certain places and when they're not. And then also to tell how fast they're going at certain areas. And so outside of that, let me rewind this because they're primarily back here. So this space that's here essentially is like where most of that information is then fed back into a central processing area that tells it when to do certain actions, like flipping different types of switches for different types of interactions. So it's a pretty important piece just because it has a large part in telling both speed, direction, and where the car is located at and what's going on. So it's a pretty important piece when it comes to classification yards and just overall in general. So going into the raw data here. So everything is fed back because we can't necessarily, we looked at the idea of essentially having some sort of processing in between because there's different architectures that allow processing in between before it gets to the central computing node that has everything in it. But we didn't want to interrupt it because it's a safety critical system. And so we went with pulling the information from the central processing node after the fact. And so the reason why this didn't necessarily cause too big of a pain was mostly just due to the fact that it had a lot more computing power, and based on its operating system, it was able to allow us to do this because it essentially was able to acknowledge when it could give us the data and when it couldn't. So outside of that, so the raw data, it comes in like this. The biggest thing is this event time, and then this is essentially the name of the device itself, and then what state it's in, and then this leading edge, trailing edge. So the leading edge is essentially when you go back to the wheel detector and it's hitting that first node of the wheel detector device, and then the trailing edge is when it hits the second one. It helps us determine where it's at and being able to use different types of indicators of just signals for us to understand when we should be making certain calculations. And so we're able to essentially take this data and determine essentially when it hit the first head on the device and then when it hit the second device, head on this second device. Wow, hit the second head on the device. And so from there, we're able to determine the speed and direction using the event times and being able to process that. And then also we're able to, because the head distance is actually a fixed number and it's typically, it doesn't stray, especially device to device, it typically doesn't vary all that much. But for the most part, we're able to actually determine whether or not the device is installed improperly, and then also determine whether or not it's defective. So this was our biggest goal, was determining if it was defective or installed improperly and not falling within the bounds of what we determined was acceptable for a device. And so one of the big things here is we were able to generate some reports. So this was one of the first set of reports that we generated from the first iteration architecture. And then we moved to more of a dashboard type situation that looks very similar to this. But essentially what happened was we were able to use these distributions of data because we would collect 30 runs over 30 to 50 runs of data to actually make these distributions to understand whether or not the wheel detector was misconfigured or needs to be reconfigured, or it was improperly installed, or if it was just a defective device altogether. So these are just kind of the different plots that you see. So it's just good to see that they fall within certain bounds. So the first head has to be within inside. It can't be lower than like this 0.8 region, and then the second head can't be more than this 0.2 or 1.2. And so that kind of was one of the big things that helped us understand whether or not it was defective. So if it was outside of those bounds, at least the distribution center was outside those bounds, it was a sign of indicator for us to go in and say, okay, you need to have someone go and have the teams that were out in the field to go out and fix those devices. And so that was kind of our primary goal, was to find those different types of problems and then be able to report them to those individuals so they can get it fixed more quickly. When the project was first started, it was kind of a battle to determine what was broken and what was not. And so, oops, too far. So we essentially were trying to make it so we had data that drove these decisions and worked with the engineers that were out in the field to help them understand why we believed it was broken versus just telling them that it was broken. And so it just kind of both relieved those relationships and brought us more together to have a better understanding and focus on what was out in the field. So going into that, so one of the other things that kind of came to mind was, did we really need machine learning for this? For the most part, we didn't. A lot of it was just that pure statistics and probabilities to determine whether or not something was broken. But we also wanted to understand, okay, with the data that was coming in, could we make predictions and say, this device is most likely going to fail or needs to be reconfigured? Because after a certain point in time, those devices did need to be just recalibrated, and it would essentially fix the problem from, I would say, 90 to 95% of anything that came in. And so we really wanted to have some ability to be able to predict that. And so that was kind of what helped us introduce certain pieces into that architecture. So going into it, at first, there was no architecture like this. There was just people pulling logs, looking at raw information and making determinations based off of pure gut instinct. And there wasn't necessarily any like pure facts or statistics behind it. And then they introduced this first architecture. And so what happened was all the files were stored out on these PCs out in the field. And then we had a process that would essentially pull all the files that we needed back to a central server. And we would run a cron job that executed a Python script that would essentially both generate the report and email it out. And then it would also indicate which ones were essentially broken. And from there, they would take the report and find out and go out into the field and understand which ones they needed to fix. And so from there, it was kind of a pain too, because the report only ran daily. And so it was kind of there was a major lag time between what was understood as broken and what wasn't needed to be essentially addressed. And so a lot of those wheel detectors that are out there really affected how the yard performed and efficiency and how well it was able to get cars going through the yard itself. And so that's why having those fixed, it helped to speed up efficiency essentially. And so having that lag of breakage to fix time really impacted the efficiency of the yard. And so we were trying to address that. So we introduced a new architecture that introduced stream processing. This involved kind of a very similar fashion, but we had to write special code because of the operating system that was out here is not a standard operating system. It was a real-time operating system. And so we had to write in C++, a special adapter that would be able to read the logs, but not interrupt the critical system. And then on top of that, deal with the different types of scenarios that would occur if it lost connection to, we used just essentially a form of JMS to send the messages back to the enterprise. And so we had to write all the logic for that and incorporate that inside the actual software that was out there. And so once that was, the messages were essentially sent over JMS, they landed on this Flink cluster. And so Flink was able to receive that and process those messages and do a lot of the different analytics and analysis of that data pretty quickly because we used Beam as the SDK that went on top of it. And so from there, we were able to essentially be able to generate the normal statistics we were doing with the Python script and store it both inside a Cassandra DB, and then we also stored it inside of an Influx DB because at the point in time, Grafana doesn't, I think even still today, Grafana doesn't have a connection to Cassandra to be able to report stuff off of, but it does for Influx DB, and they kind of have very similar purposes. And so we had Influx DB as our DB for reporting information back and be able to tell, okay, here are the distribution and here are the ones that we believe that are broken. And so that's what this was essentially for. And it reported back to a dashboard that the yards essentially had up on a TV that they could get live reports of what was broken out in the yard. And so And then also they still received an email. A lot of this typically went to the higher ups to understand, okay, what was broken in their yard and what are their techs doing out there to fix it. So another thing that fit into this architecture was the Cassandra DB, and essentially how that fit in was with the machine learning pipeline that we built and machine learning APIs. So at this point in time, machine learning pipeline is funny because they had just released Kubeflow and other like frameworks that were like very similar to that to allow for machine learning pipeline to be easier. So we had to build kind of our own, and it wasn't as efficient as I would have liked, but it kind of worked for the purpose that we needed it to, because we didn't really change these algorithms all that much, and essentially the models. But essentially we build those models with this pipeline. There's a lot of analysis and manual process that kind of had to go into here. But at the end of the day, once a model was created, we were able to deploy it through just a Flask API. We didn't really have anything else that would allow us to deploy it at the point in time. So we just made this APIs that were pretty rudimentary at the point in time. So this was probably many years ago. I can't even remember. I think it's 4 or 5 years ago. So, but essentially the Flink cluster would also interact with those APIs to help it understand here what I see as from a distribution perspective as broken. And then also based on the live data that's coming into here, it would also make requests to the APIs to see if, based on the information that it had, could it determine whether or not something was broken. And so we used the two data sets that we achieved from both the API and then also the distribution to help us understand what is the overlap in what we thought was going to be broken and what is actually broken. And so we reported that, and then that just came back to the yards. And so there was a lot of different moving pieces in there, but for the most part, the bread and butter was this Flink cluster, and it just, the way that it was able to process data and at the speeds, because these yards go 24/7, they literally don't stop. They don't stop on holidays. They just are constantly processing cars. And so we get wheel detector data pretty much all the time. And they had, I can't say the number of yards because it's, I think that's supposed to be secret. I don't know. But essentially, they had a lot of yards that they were pulling data from, and they were always pulling data. So I can't remember what the level of data was, but it was significant. It was no small number, because we also looked not only at wheel detectors, we looked at other devices that they had out in the field. So there was always data being streamed in and pulled in and understood as what was broken, what was fixed, what was seen as a potential risk. So there was always data being pulled in, and the way that Flink and Apache Beam just kind of work together and are able to process things, and it makes it easy because you can write code in Java, Go, and Python. It just makes it super easy to use from a standpoint for other people too. So definitely, if you're ever considering processing lots of data at significant amounts of data at really quickly, I would definitely look at Flink and Beam as a potential set of SDK and framework, or essentially a framework to use to do all that. So there's a lot of really good connectors too that are out there. So outside of that, going to the next part here. So results. So one of the biggest things that we were able to do is really significantly reduce the failure time to repair. I can't say how much, just because I think I'm not allowed to, but regardless, it was a significant amount of time. I think that for one example that I encountered, it was broken and we acknowledged it. I think it was in about 2 minutes since the event. And then it was fixed in, I think, just shortly after that, maybe 30 minutes, just because the tech has to get the signal and then also go out there and fix it. And there's a bunch of other little things that go out with that too. But regardless, that also leads into like the second result, essentially, increased safety of the yards and efficiency. Just the aspect of those wheel detectors help the yard masters, is what they're called, determine where the cars are going and whether or not maintenance crews or technicians can go out in the field. And so it really helps with the system to be able to control different pieces that really are crucial to the yard overall. So the biggest thing was just the productivity and reducing errors inside that classification system and making it so that cars were in the right places at the right times, and essentially let us be able to create this system that was more efficient overall. So it was just really nice to be able to incorporate some sort of analytics to help both the engineers that were processing the data to understand what's going on, and then also help the technicians understand why we're making these decisions and why we need certain things fixed. So other than that, and then so the next slide is going to be questions. Kind of a quick presentation, but for the most part, a lot of it just comes down to the architecture. So and what was used. Any questions?
We've got a couple so far.
Cool.
The first one is, at the beginning of your presentation, you were showing some of the data, and this person's asking, is there a reason why each row appears to be duplicated, or why there's some what looks like pairs of records?
Yeah, so essentially what's happening here is, so this is the first head. Even though this is H1, it's actually the second head. So we called them H0, H1. But so this is the wheel that is going over, and then so this is the leading edge. So it essentially, let me see if I can point to it here. So it'll signal once the leading edge is here, and this is a leading edge. And so once it rolls over here, once this gets to like here, you'll see these are the two leading edges. And so that's what it's indicating for that wheel detector. And then the trailing edges are over here. It just signals to it that this head is turned on and turned off. And so when we look at this, so this is the state of that head 1 turning on, and this is the state of it turning off. And so that just allows us to understand where the wheel is at and be able to run different types of calculations with this essentially, or with just like the time difference. And then the distance between these two heads is fixed. And so we're able to calculate the speed and then understand whether or not it's processing it correctly. And then also based on these distributions and how high some of these peaks are, we can tell whether or not the device is off center on the rail or not, because typically what happens is when they install these, they drill this huge hole through the rail and then they install it, and there's a clamp on the other side that holds it. But that can make it so it tilts and gets off center, and then it's not properly reading anything. And so it can kind of mess things up with the overall system. And so that's kind of the reason why that it looks like there's duplicate records. And then also you'll see that it'll happen in reverse. And so I'm trying to see if I can find one. I don't think I have one on here. But essentially they can happen in reverse. And what that means is that they're just going the opposite direction. So instead of the wheel going this way, it's actually going backwards. And so that makes it kind of nice in the sense that why the records are kind of duplicates. But when you're going through the pre-processing, essentially we had to account for that. We have to make these separations between all the data and understand when is it actually going backwards or when is it going forwards. And so one of the struggles that we had was when a car kind of stops on top of it, and it essentially stops like right here, and it's kind of rolling back and forth, which can happen. It kind of sends these really odd signals, and so we had to figure out a way, what was the best way for us to go about removing those types of data to make sure that it wasn't affecting our decision on whether or not we thought it was broken or fixed, or just in general wasn't reporting properly. And so a lot of that had to go with a lot of analysis. So it goes back to the data analytics and understanding, okay, here are all our good situations, and then here's kind of the ones where we can see that it's obviously not, something was happening in the sense they were rolling back and forth on top of it and wasn't essentially something that we want to consider as valid data. And so there was a process to go in and filter out those types of situations too.
All right, got another one. If you were starting this again from scratch, what changes to the architecture would you make given new tools available, lessons learned, etc.?
Oh, I totally use Kafka, but the company that we were at, they did not like Kafka, and they had their own version of it, and it just, they weren't big fans of it. I don't know why. They had some reason, but I don't think it was a good one. But Kafka is definitely something that I would definitely bring into this, just because it has better integrations with Apache Flink and Beam, and just being able to do sort of like stream processing beforehand is kind of nice. There's a whole bunch of different things, I guess, I probably would have included. Oh, I definitely have Kubeflow. Kubeflow is probably one of the big things for the machine learning pipeline. And on top of that, it helps with being able to present those APIs for you and be able to interact with that. I would definitely want that, just because this whole process here was the biggest pain. I think I spent way too many hours trying to figure out how to do this efficiently and make it so it wasn't something where I had to constantly manage it every day. So Kubeflow would have fixed all of these two pieces specifically. That would have made life significantly easier for me. And then for this reporting cluster, I probably would have just stuck with Grafana and Influx, or built it so it could interact with Cassandra. That would have been really nice. But essentially, there was a lot more to this reporting cluster than there was just to having it as Grafana, because there was other feeds that were telling it essentially what was going on and what was broken. And so there was a lot of complex logic inside of here to present just the data and dashboard. But we used Grafana for more of, it was more for the engineers, for us to understand more low level information about what was occurring and what was happening. The reporting cluster, we actually had to create a custom dashboard built in Angular, and we just had Java APIs that were interacting with it, pulling information off of a Oracle database, essentially, that allowed us to have a lot of different information. But we had to build a custom application just to do this reporting out to here. But if I had to go back and do it again, I would probably just keep it to Grafana, just because of how easy that integration is and how you can modify the metrics pretty easily, and how easy is it to essentially have that dashboard out everywhere else. So outside of that, I don't know. I guess one other thing I did was I used, at the time, it was sklearn, or scikit-learn, sorry. That was the Python library that I used for the machine learning. I would totally use TensorFlow now, just mostly because I prefer TensorFlow, and it's a little bit more versatile and it's more scalable when it comes to different types of applications. So, and the level of data that we had inside this Cassandra DB was sufficient enough to use TensorFlow versus scikit-learn. Scikit-learn, it just wasn't optimized enough to be able to handle that much data. And so that was one of the big struggles too, was just making the APIs efficient enough and come back in a more timely manner. So.
All right.
Yep.
Let's say I'm watching this talk just because I think machine learning and AI is cool, but I don't really know much about it, or don't know how to, get started. Would I need special hardware, special software? Kind of walk me through how I would kind of get into machine learning.
Yep. So I would say it kind of depends. From my perspective, I'm very biased towards more mathematical based approaches, just due to the fact that my undergraduate was in physics, and so I did a lot of math there, and so it was more applicable for me to look at it from the math perspective. And so TensorFlow is more in that sense, where it's more in that math based and understanding that math. Well, TensorFlow, and then so there is this group called Deep Learning AI, and so they have really good courses that essentially allow you to learn all about this, but they're more math centric. if you're not into that whole math-centric aspect, I would definitely look at Fast AI. They use PyTorch. And so that's the Facebook machine learning libraries that they have, framework rather. But they're both really great. Deep learning AI is my personal favorite, just because that's where I got my start. And they were kind of the ones who introduced machine learning to me, because I mean, when I first started this job, I started to get into the very rudimentary aspects of machine learning and just learning about regressions. Regressions are your most basic aspect of machine learning. And so I loved that aspect of it. So I wanted to continue to learn more. And so that's how I kind of got into it, was going into the deep learning stuff, deep learning AI courses that they had out there. It's all done through Coursera. And so they have labs and a bunch of other stuff in there, but they really talk about, from a math perspective and from a statistical standpoint, of the importances of different pieces inside of machine learning. So I definitely recommend going to deeplearning.ai. It's a website. And then if you want to do the math-based approach, and then if you're looking to not do the math-based approach and kind of go from more of a practical standpoint of using it, I'd definitely check out Fast AI, because the PyTorch is, and how they've constructed that course is a lot more well suited for individuals who don't want to get deep into the math. So, but I'm a nerd for that type of stuff, so I like the math and understanding that. So if you want to do that, I definitely recommend deep learning AI too. So that would be the two things that I would try to focus on first, because it definitely give you the foundation that you need. And then from there, I would definitely start looking at different types of certifications, like the Google certification, and then the Azure, and then AWS too. So I've done all three, and they're all really great, and they all have their different strengths, and they all have their weaknesses. So, but they're all really great because they all teach you different things. So.
Cool. That is all the questions we have.
Cool. Sounds good. Yeah. If anybody ever has any questions, feel free to reach out to me, email me, or internally you can message me as well. So